Hey, what is a star made of? Like the sun and all those twinkly ones at night. They look so solid and fiery.
That's a great question. Stars aren't solid like rocks or balls of fire you might imagine. They're actually huge balls of gas, mostly made up of two simple elements, hydrogen and helium. Hydrogen is the lightest gas, like the stuff in balloons that floats them up. And helium is what makes your voice squeaky if you breathe it in. But inside a star, this gas gets super hot and turns into something called plasma. Think of it as gas that's so energized, its particles are zipping around like a wild party, carrying electricity.
Gas? But stars look all bright and round, not fluffy like clouds. How can gas hold together like that?
I get why you'd think that. It's easy to picture stars as hard fireballs from stories or drawings. But imagine a giant cloud of cotton candy, squished together by an invisible force called gravity. That's what pulls all that hydrogen and helium into a tight ball. Our sun, for example, is about 70% hydrogen and 28% helium, with just a tiny bit of other stuff like oxygen or iron sprinkled in. No solids at all. It's all swirling gas under insane pressure, hotter than anything we know on Earth, millions of degrees in the core.
Whoa, millions of degrees? So no rocks or metal inside?
Nope, nothing like that. Stars form from clouds of gas and dust floating in space. Gravity tugs those clouds together until they collapse and heat up, starting the star's life. Remember the Big Bang? Way back then, the universe was mostly hydrogen, with some helium popping up early on. That's why stars are built from those basics. If you could zoom inside the sun, you'd see layers of this plasma gas, denser near the center, like a cosmic onion, but way hotter and brighter.
Okay, that makes sense. But why don't they just float apart if they're gas?
Good point. Gravity is the hero here. It's the pull from all that mass keeping everything squeezed tight. Picture kids on a playground, holding hands in a circle, spinning faster and faster. They stick together because of the motion and pull. In a star, the gas is so massive, billions of times Earth's weight, that gravity wins the tug-of-war against the heat trying to push it out. That's why stars stay round and stable for billions of years. Scientists figured this out by watching how stars form in telescopes, seeing those gas clouds collapse into new stars.
Billions of years? That's crazy long. So, mostly hydrogen and helium. Got it.
Exactly. You've nailed the basics. But here's something cool. All that gas doesn't just sit there. It has to do something to make the star shine so bright. I wonder what turns those simple gases into all that glow.
Yeah, that's what I was wondering too. If it's just gas, like hydrogen and helium, how does it light up the whole night sky? It doesn't seem like it could burn forever, like a campfire.
You're right. Stars aren't burning like a log on a fire, where oxygen makes things crackle and smoke. That kind of fire would fizzle out way too quick for something as huge as a star. Instead, inside a star's superhot core, something amazing happens called nuclear fusion. Picture this. The intense heat and pressure from all that squished gas smash hydrogen atoms together, like kids piling into a too-small fort during a game of hide-and-seek. When 4 hydrogen atoms combine, they turn into 1 helium atom, and in that squeeze, a tiny bit of their mass gets converted into a massive burst of energy, light and heat that blasts outward.
Nuclear fusion? That sounds like something from a science lab, not space. Does it really make the star glow?
Oh, it totally does, and it's way cooler than a lab experiment. Think of it like rubbing sticks together to start a fire, but on a cosmic scale, except instead of friction, it's atomic particles slamming at speeds we can't even imagine. This fusion process releases energy in the form of photons, those little packets of light that travel out from the core, bouncing around the star's layers until they escape as the glow we see. Our sun fuses about 600 million tons of hydrogen into helium every second, pouring out enough energy to power life on Earth. Without it, stars would be dark and cold, just big blobs of gas drifting around.
Every second? Whoa, that's a lot. So the glow comes from changing one gas into another, not actual burning?
Exactly. It's not chemical burning like a candle wick. It's nuclear, deep in the atoms themselves. Helium is a bit heavier, so when hydrogen fuses into it, that extra weight difference turns into pure energy, following Einstein's famous E=mc² idea. Energy equals mass times the speed of light squared. It's efficient, too. That's why stars can shine steadily for billions of years without running out of fuel right away. Imagine a star as a giant, slow-cooking oven where the ingredients rearrange to keep the warmth going, lighting up planets far away.
Like a never-ending pizza party where the dough turns into cheese or something. Okay, I get how it produces light now. But is the helium just sitting there after? Or does it do more?
Great analogy. Yeah, the helium builds up in the core like leftovers from the party. As a star ages, it starts fusing helium into heavier elements. But hydrogen is the main starter fuel. This whole fusion chain is what makes stars the powerhouses of the universe, creating not just light, but the stuff that eventually forms planets and even us. Without that glow from fusion, nighttime would be pitch black. No twinkles at all.
That makes stars sound alive almost, changing themselves to shine. So we see the light, but how do people on Earth really know all this is happening inside?
Stars do feel almost magical that way, don't they? But scientists aren't just guessing about what's inside. They've got clever ways to spy on them from way down here on Earth. The main tool is something called spectroscopy, which is basically like using a super-powered rainbow maker to break down the light stars send us. Imagine holding a prism up to sunlight and seeing all those colors split apart. Well, telescopes do that with starlight, but way more precisely, revealing hidden clues about the elements burning inside.
Spectroscopy? Sounds fancy. So the light tells us what's in there, even though we can't poke it with a stick?
Yep, exactly. Light is the ultimate messenger from across space. Each element, like hydrogen or helium, absorbs and emits light at specific wavelengths, creating unique patterns called spectral lines. It's like a barcode for atoms. Hydrogen has dark lines in the blue and red parts of the spectrum, while helium shows up with yellow ones. Astronomers capture this with instruments on telescopes, like the ones at places such as Mauna Kea in Hawaii, and compare them to lab tests on Earth. If the patterns match, boom, we know that star's got the same stuff as our sun. No need to send a spaceship. The light travels billions of miles to spill the secrets.
Whoa, like fingerprints for gases? But stars are so far. Doesn't the light get all mixed up on the way?
That's a smart worry. Space is vast, and light does stretch out as stars move. But scientists account for that with something called redshift. Kinda like how a siren's pitch drops as an ambulance zooms past. They measure the shift in those spectral lines to figure out distance and speed, too. Take the star Betelgeuse in Orion. Its spectrum screams, Mostly hydrogen and helium, with some heavier metals, even though it's over 600 light years away. We've been doing this since the 1800s, thanks to folks like Joseph Fraunhofer, who first spotted those lines in sunlight. It's not perfect, we can't see every layer, but it paints a clear picture of the core's composition.
Redshift, like the ambulance thing? Cool, I get how they decode the light now. So that's why we know it's not like cheese or something silly inside.
No cosmic cheese, thankfully. Spectroscopy has confirmed stars across the galaxy are mostly the same basics, with variations based on age or size. Young stars are hydrogen-rich, while older ones show more helium buildup. It's revolutionized astronomy. Without it, we'd still think stars were mysterious fire holes. But it makes you think. Our sun works this way because of hydrogen and helium. But what if a star formed with totally different ingredients? Would it even shine the same?
Different ingredients? Like if it was made of iron or water or something. What would that do?
Oh, that's a fun what-if to explore. Stars made of iron or water instead of those light gases? Well, let's think about it step by step. First off, stars form from massive clouds of gas in space, pulled together by gravity, that invisible force we talked about earlier. But if that cloud was mostly heavy stuff like iron, say from exploded old stars or something rocky, it wouldn't behave the same way. Gravity would still try to squeeze it, but iron atoms are way bulkier and don't get as hot or squishy under pressure. Picture trying to pack a bunch of heavy bricks into a snowball. It just doesn't compress right, and without that tight squeeze, you couldn't reach the temperatures needed for fusion to kick in.
So, no fusion if it's iron? Like, it would just stay a cold lump?
Pretty much. Fusion, remember, thrives on light elements like hydrogen because their nuclei are simple and can smash together easily in the heat. Iron is at the end of the fusion chain. It's what stars make after burning through lighter stuff. But fusing iron actually sucks energy away instead of giving it out. If a star tried to form mostly from iron, it might collapse into a dense ball, like a mini black hole or a neutron star. But it wouldn't glow steadily like our sun. No light show. It'd be dark and short-lived, maybe fizzling out in seconds rather than shining for billions of years. Scientists see these failed stars sometimes, called brown dwarfs, but they're dim and chilly because they can't fuse enough.
Brown dwarfs? Those sound kind of sad. What about water? Could a star be made of that? Like a giant ice ball that melts?
A watery star would be wild to imagine, but water's mostly hydrogen and oxygen's heavier than helium. Gravity could pull a water cloud together, heating it up to steam or plasma, but fusion would struggle. Hydrogen and water might fuse a bit at first, but the oxygen would gum up the works, making the core cooler and reactions slower. It'd burn brighter at the start, maybe like a supernova burst, but then poof, way shorter life, maybe just millions of years instead of billions. Our universe doesn't have many water-rich clouds big enough anyway. Most are pure hydrogen from the early cosmos. Heavier elements just make stars puff up and die faster. Like revving a car engine too hard, it overheats quick.
So light gases are perfect for long-burning stars. If everything was heavier, the sky would be empty fast?
You got it. Exactly why the universe favors hydrogen and helium. They're leftovers from the Big Bang, easy to fuse, and keep stars stable and long-lasting. Without them, no steady light for planets to orbit, no solar systems forming from the leftovers. It's like the universe's recipe for endurance. Start simple to go the distance. We've modeled this in computers, simulating weird stars, and they always end up unstable, exploding or collapsing too soon. Real stars stick to the light stuff, which is why the night sky sparkles with such reliable twinkles.
That clicks now. Stars have to be mostly hydrogen and helium to shine right and last. It's all connected. The gases, the fusion, the light we see.
Precisely, and you've pieced it all together beautifully, from the basic makeup to how they glow and what we'd miss without it. Stars are these incredible engines of the cosmos, turning simple stuff into the wonder we gaze at every night.